want to welcome everyone to a joint presentation with the Energy Conservatory and TruTech Tools. And I'm Bill Spohn with TruTech Tools. That's fine. We'll just go with that. We're trying to do things here with like 4 different computers and 3 different people and 3 different cities. So please bear with us, but it's going to be fun for us, hopefully for you too. So this is a picture of me. This is what I do at TruTech, and I really enjoy working with other smart people in the field, and there's a lot of smart people at Tech. Steve, why don't you introduce yourself as one of those smart people?
Thanks, Bill. This is Steve Rogers. I'm the president of TEC, or the Energy Conservatory, and you can see a little bit of information about me. And I'm happy to be here today to talk about building pressure measurements. And we're going to actually do some live demonstrations of how to make those measurements. Hopefully that'll be informative. And back to you, Bill, to give an intro to TruTech Tools.
Sure. So TruTech Tools, we founded in 2007 with Jim Bergman Sr. and Jr., and Jim Bergman Sr. unfortunately has passed. But it's a great company following a great philosophy to really help educate and train the industry and sell some tools along the way to have fun, as Eric Preston likes to say a lot. Right now we have 18 employees. That's a picture taken in June, I think, of 2019. So we've got a few more people than that picture shows there. We have over 85 brands of products. You see on the right-hand side there a picture of our warehouse where we serve the industry with as a stocking distributor with over $1 million in inventory. We also ship 7 days a week, so we really try to provide a great customer service. And of course, we have a lot of tools and test instruments, including blower doors, duct leakage testers, and combustion analyzers, digital gauges, et cetera. So we're really all about trying to help technicians do better work around the country.
Great, thanks, Bill. Okay, so I'm going to give a little bit of background about the Energy Conservatory now. If you've heard of our company before, you're probably familiar with our Minneapolis blower door or Minneapolis duct blaster. Maybe you've seen the DG-700 digital manometer that's been around for a long time now. Our newer manometer is the DG-1000, shown kind of center left there at the bottom. And then on the other hand, the right-hand side here is a little bit of an introduction of some of the products that are more focused on HVAC air measurements. So air pressures and air flows, if you want to know the air flow or the flow through an air handler or an exhaust fan flow meter, how much ventilation are you getting? That's what the right hand is focused on. But underneath it all, we're really trying to make it easier to get it right. That's what we're all about at the Energy Conservatory, is helping people make better measurements of airflow, leakage, pressure, et cetera. Today, we're going to talk about a new product that was released just at the end of last year. It's called the DG-8. And this is a cost-effective, highly accurate single-channel manometer. If you're familiar with blower door manometers, you might know that there's something different about a blower door manometer than a standard technician's manometer that's used for static pressure measurements, for example. A blower door manometer is capable of measuring tiny, tiny pressures accurately, and that's what has been required to make most of the measurements we're going to talk about today. What's different about this product is that instead of costing, upwards of $1,500 for a blower door manometer, this manometer is only $549, and it has the same accuracy as those highly accurate blower door manometers. So we're going to talk today about what you can do with that kind of accuracy. There's some very interesting measurements that can really help you figure out what's going on in some key situations. So that's what today's webinar is all about. Before we dive into those applications, I just want to give a little bit of a comparison between the DG-1000 and the DG-8 so that you understand the difference. As I said, that they have the same accuracy, but what you can do with them is a little bit different. If you need to do a blower door test or a duct leakage test with our duct blaster, you're going to want the DG-1000. That's got the built-in capability to measure the airflow, do the airflow calculations with the fan. And so that's the one you want for those measurements. But either one of them can do these bottom 3 measurements, which are room pressure measurements that Bill Spohn Sr. is going to demonstrate that for us today. Zonal pressure diagnostics, if you're into measuring sub-slab pressures for radon, they can both do that. We'll talk about some more things that you can measure as well. So if you just need a pressure, highly accurate, small pressure, either one will do. If you need to do a blower door or duct blaster measurement, you're going to want the DG-1000. Okay, so here's a list of the pressures that we're going to talk about today, time permitting. We're going to start at the top here, but because we're doing some live demonstrations, I'll give you just a little bit of advance warning. We might not get to everything. We're going to start with kind of what we think are the most interesting, the most important, which are room pressures and house depressurization. And then we're going to talk about measuring draft pressures and combustion appliance zone safety pressures. And then we'll get into static pressures of air handling equipment. We'll look at the exhaust fan flow meter and take a look at zonal pressures, how those are done, and pressure pan measurements. And if, with the exception of the middle one, the static pressures, all of these really require a precision micromanometer that's capable of measuring, a few pascals, which is into thousandths of an inch of water. Okay, so let's start with room pressurization. When and why would you want to measure room pressurizations? Well, this can be a good first step to understand some particular occupant comfort issues. When we talk about room pressurization as opposed to the whole house, we're really talking about is the supply airflow that goes into a bedroom, does it have an adequate path back to the return without causing a large pressure difference? And this can happen because residential air handlers can move a lot of air, depending on the size, something between 500 and 2000 CFM. And if you have pressure imbalances, it can drive infiltration. It can change the amount of supply air that's getting to a bedroom. And these measurements or these things can also affect indoor air quality. There can be actually combustion safety issues. So this is what we're going to get into. Okay, I'm going to pass it back to Bill for just a second here. If you want to walk us through, tell us about your home. Many of the participants may have heard about your personalized performance home.
Sure. Thanks, Steve. Marilyn and I decided to build our first and last house a couple of years ago. We found a nice plot of land, as you can see in that picture there, from a drone's eye view. We have very high efficiency house, personalized performance, I call it, because one of our goals was aesthetics, but it was also comfort, and then indoor air quality and energy efficiency. So there's a lot of things going on here, a lot of things cutting edge, things have a lot of complicated things come together. We do have, as we go through the testing today, you'll see some large connections between the first and the second floor. There's a huge vaulted opening, which is in that picture in the upper right-hand corner of the frame there, where the sort of the upstairs lounge area, we call it, connects to the living room area. So there's a lot of pressure and thermal and air energy moving between the two. The snow scene there in the lower left-hand corner gives you an idea of what the scene is, what the setting is for the house, and the fact that we have some really good blower door test numbers, some really good thermal isolation. You don't see any melt through on any of the roof lines, anything like that, unless it's caused by the sun coming from the outside. None of the heat inside. Very little of the heat inside gets out. And then in the right-hand frame there, this is actually a model of the house that was done by Russell King, who has a product called Quick Model. That's a really awesome program for doing energy load calculations, duct design for homes. He did it for me with some actual measurements to give me exact and specific volume and square footage area calculations to help me get the blower door ACH 50 number down. So the upstairs bedrooms are on a single zone. The whole upstairs is on one single zone, so it's a 4-zone house. The first floor has 2 zones. Mainly it's the office and the bedroom on one, the rest of the first floor on another, and the basement is all one zone unto itself.
Okay, and also importantly, it's an all-electric home, right?
That's correct. Yeah, there's we're trying to run off of only solar. We'll let you know about that in about a year if we make it that far. But yeah, there are no gas appliances, no gas heating, nothing gas inside the house.
Great. And we'll see that that makes a difference in some of the stuff we're measuring today. My house is not, and we'll see why that's important in my house, that these pressures are more important in my house than they are in Bill's house. Okay, so the first thing that we want to do here is demonstrate a room pressure and show how that's measured. The purpose of this measurement is to understand if there is an adequate path for the supply air that's entering the bedroom to get back to where the return is located. And so Bill's going to demonstrate this. We'll pause the presentation for a minute, and he's going to measure the pressure in the upstairs bedroom with respect to the main, that lounge area that he mentioned, because that's where the return is. We need to see, can the airflow get from the supply to the return without a lot of resistance? So I'm going to go ahead and pause the presentation, and then hopefully Bill's ready to show a live demo of actually making this measurement, and then we'll talk about what it means.
So I've powered up the DG-8. I'm going to walk over to one of the bedrooms. And right now I have all the ventilation systems off. The house has a ERV as well as a HAC system. So I can bring it up on a bigger screen here.
So now he's going to turn the HVAC system on, get the air flowing, and we'll see if that room starts to get pressurized.
So Steve, would you like just the zone to be turned on or the whole house?
I think just the zone is fine.
Okay.
Up to,
I'm turning up the thermostat remotely. Heat mode, we're reading 72 on this stat. I bumped it up to 79. Okay, it's cranking on now. And I got to put the hose back under the door. We should start to hear it blow in a minute. But while we're sitting here watching and waiting, I'll go ahead and show you the ERV system. Actually has remote control on it, and I've turned it off. So right now it's reading those conditions, but there's no airflow running.
Hey, Bill, somebody asked, is it a water cooled or a heated ERV? Water cooled.
It's got a heat pump in it.
Sorry.
Yeah.
Okay.
There's a 1/3 of a ton heat pump inside the house, inside the box. It's called a conditioning ERV by Build Equinox. And it has separate ECM motors for both the supply and the exhaust air.
And another question that's coming in while we're waiting for that. Won't heat mode be a slower fan speed and therefore less delta P?
Well, heat mode's going to be what it is. So right now I put it on high demand, like we want 79 up here and it's only 72. But the zone system is going to take a couple minutes to respond.
Yeah, so
noise?
Part of the answer to that question is where Bill has intentionally cranked the heat way up because we want to see, is there an imbalance when it's in the highest heating speed? If it were in a normal heating speed, yes, there might be less pressure imbalance, but we want to know what the worst case is when it's in high heat.
We're starting to hear a little bit of fan noise up here.
And just so we know, Bill, how long does it take for that to ramp up to that high heat? Does it take?
It may take 4 minutes when I
Okay.
did the testing the other day. While we're at it, I'm just going to take a walk down here and show you where the return is. So first, take a look down here. So this is the open connected area. So everybody kind of gets an idea and picture that as. So this is very connected to zone 1 and actually zone 2. If we go over here, you can see this is the return, which needs to be dusted a little. It's on the second floor. So this is where the return's coming. There's only one return per floor. A return on the first floor, second floor, and basement. Also, we're not seeing any change. And I'm walking around with the tablet, which is giving me the Bluetooth reading from the DG-8, which makes it really convenient to use. And I'm seeing no change at all. I'm also
Did you measure this before, Bill?
I didn't do one before. So I'm going to crank up the other zones, Steve, just to see if I can make something happen. Okay, now I got all 4 zones lit up. Yeah.
And I saw a question come through the chat asking what was the intended return path. And I think the answer is that because this is a really efficient home and the heating and cooling flows are so low, it's really just the door undercuts and leakage around the door through the walls. That's the
exactly. Let me show you over here on the wall. These are 2 supply vents. And they produce max 30 CFM each. So there isn't a lot of heating or cooling load necessary due to the type of construction here.
So Bill, we got a question. Isn't that a return grill above the door? I think the answer is no, that's the return for the whole floor.
That's the return for the whole floor. Yeah.
That doesn't go through to the bedroom, that goes down to the HVAC unit.
Correct. So if you could just point on here, Marilyn. This is the return path. And just so you can see here, we're getting very little differential. As Steve had mentioned, with maybe 60 CFM flowing into that space, a small slot like that doesn't provide tremendous restriction.
Yeah, so is there a way for you to tell if we're up to the full speed yet, Bill?
It sounds like it.
Sounds like something's happening.
Yeah, we've got.
Bill, what's the tonnage and the duct size of the system?
The tonnage is 2 tons for both heating and cooling, more or less within like 10%. And that's the load calculation for the house was 2 tons of heating and cooling. And the duct size, you mean the diameter of those ducts? They're 2.5 inch, basically thermoflex ducts, if you look that up. So it's somewhat insulated, spiral rigid, very well sealed ducts that are more like hoses.
Yeah.
Gotcha.
So let's keep moving then. I think what we've confirmed here is that there's no room pressurization that's measurable, not even a tenth of a Pascal. No. And that little burst there was from opening the door, I imagine, or moving the hose.
Oh no, I stepped in a hose.
Oh, that'll do it. Okay, so let me go back to sharing the presentation, and we'll introduce the next measurement that we want to make.
Right. Give me conditions to set up so I can be ahead of the game here.
He's got it up there, so I think he's good.
Yeah, actually, so preparing for the next measurement, Bill, we're going to measure the house pressure with respect to outside. So probably what will work there is leave it running in full speed. And then when we get to that measurement, rather than turning it on, we'll turn it off.
Okay, very good.
Yeah. Okay, so coming back to our presentation here. So what Bill confirmed is that in that bedroom, there's no problem, the undercuts of the door, leakage around the door, or, through the cracks under the bottom plate of the stud wall is enough for that small airflow required to heat that room and cool that room. That's plenty of leakage area for the conditioning airflow to get back to the return back in that main lounge area, as Bill mentioned. Okay, so the next thing we're going to talk about is house depressurization. So we want to talk about this because house depressurization can be a really big problem. And this happens especially in climates where ductwork is located in, where ductwork is located in unconditioned spaces. So if you have ductwork in attics, ductwork in crawl spaces, ductwork in garages, if that ductwork is leaking, it can cause the entire house to be pressurized or depressurized only when the system runs. And that can cause some real comfort problems. And it can cause the load to be much higher than expected, so you can't achieve set point, especially if you have occupants saying things like, you know, when I have different comfort during the day than during the night, or I come out of my bedroom in the morning, the bedroom is comfortable, but the main living area is really humid in the morning. Those are things that might clue you in that you have a house depressurization situation going on. And what happens is that the mechanical system is actually driving air in or out of the house envelope. And it can cause your real loads to be much more than you would calculate in a load calculation, and it can cause significant problems with comfort. Okay, so here's what we're going to do. Normally, you'd do the baseline, you'd measure the house with respect to outside with the system off. But as I just mentioned to Bill, to make this go a little quicker, we're going to actually measure the pressure with the system on and then turn it off and see if we see a change. And we want this pressure to be less than about 1 Pascal. If it's greater than that, you could have significant problems driving infiltration, causing comfort problems, especially if the house is not very airtight. Okay, so here's how we do this measurement. You'll notice that we want to have all the interior doors in the house open, and we're going to connect the tube to the minus port of the DG-8. And the reason for that is we're actually trying to measure the pressure inside the house. And so inside the house is what's connected to the plus port on the manometer. And in the minus port, we want to measure the pressure in the house with respect to or compared to the pressure outside. So I believe Bill's got a tube set up going out through the crack in the door, and we've made sure that that tube's not pinched. And now we're going to measure house pressurization. So I'm going to stop sharing here.
So I have the DG-8 displaying, we'll call it live streaming data, just second by second. This is a 10-second average, I believe. Is that correct set up there?
Yep, that's right. So you see under the screen it says 10 second. That button allows you to change your averaging. So if you got windy conditions and it looks like there's a little bit of a breeze, the number on the DG-8 screen was bouncing around a little bit. You'll see the number on this screen is moving around way less because it's doing a longer average. And that helps if you're trying to measure these tiny pressures in breezy or windy conditions. And so the pressure that he's measuring here, minus 3.3, minus 4.2. So he's around, 3.5 or 4 pascals. And the reason for that pressure is because the air inside his house is warmer than outside. What's the temperature outside today in Pittsburgh, Bill?
It's 27, 28.
Okay.
And actually, it looks like, or it sounds like the heating system is kicked off.
Oh, okay. So it did just what we wanted.
Yeah, it kicked off. So when you were seeing 4.7, 4.8, that's the last time it was on for that 10-second average. So right now we're in off condition.
Okay. So it looks like it may have changed by maybe 0.5 Pascal to 1 Pascal or something like that. And
that validates with what I did yesterday.
Okay. So that means that there might be a little bit of leakage between it's getting, when it's running, you get more depressurization, which means you might have a supply leak to outside, which means that there's a little bit of negative pressure, a little more negative pressure when it runs. Okay, so yeah, we compare that 4.7, 4.8 pascals when it's running to, now it looks like we're, 2.5 or 3 when it's off. And that tells us there's a little bit of depressurization in the house. And so if the leakage to outside is from a supply duct, that means you're blowing more air outside, and it's going to get made up by sucking more into the return system, which actually is, the house is part of the return system. It's connecting the supply to the return. Yep, the big duct. So hopefully that gives you an idea how to make these measurements. You get the tube running out the door, you're just measuring the pressure inside the house compared to outside the house. And if that pressure changes a lot when you turn the system on and off, then you know you got leakage to outside from the ductwork.
You just do one dramatic thing and turn on the kitchen range.
Oh, right, that's right. I forgot about that one. So let's keep focused on this. So Bill's now going to turn the range hood on, and we're going to watch what happens to this pressure. Okay, we got a 10-second average on the screen on the left and real time on the right. So you can see now we're really dropping in pressure. So now the 10-second average is catching up to the other one. And so if the range hood were depressurizing your house by, we're seeing, 11 or 12 pascals, and you had naturally vented combustion appliances, this would be a major cause for concern, because this is enough pressure to cause a water heater or a naturally drafted furnace to backdraft and pour the combustion gases into the house. But Bill's all electric, as I mentioned, and so this is really not a problem. It's just telling us that the air that's going out the range hood is coming in through all the leaks, and that depressurizes the house by about 10 or 12 pascals. So when we do this house depressurization test, we really only did the first one, which is called dominant duct leakage. And we found that Bill's house was probably a little bit less than a pascal change, and it's a very tight house, so that's not a major concern, nor is it a big surprise. But if you have comfort problems, you need to be looking a little bit deeper, because if you do the same measurement with all the interior doors closed, very often the pressure will go up or down depending on where the leakage is. And that can cause more infiltration and be drawing in outdoor air, causing, humidity or cold air to come in. Okay, so next we're going to take a look at combustion appliance zone safety. So we mentioned that minus 12 pascals in Bill's house is not a problem, but if you've got a natural draft appliance, this can be a problem. We're actually going to demonstrate this in my house. I've got a natural draft water heater, and we're going to turn on some exhaust fans, and we're going to show you what happens and why this can be a significant safety issue. So how is this done? There's a couple things that you can measure with this DG-8 manometer. The first one is you can drill a hole right into the flue pipe and measure the pressure in the flue pipe. If it's drafting properly and you've got the hose connected to the plus port on the DG-8, you're going to measure a negative pressure. We're going to demonstrate this. If you're measuring a positive pressure, that means that there's actually airflow coming down the flue rather than up the flue, and the combustion gases aren't going to go up like they're supposed to. The other thing that you want to measure is measure the pressure in the room, because usually if it's backdrafting, the problem is that the pressure in the room is getting so low that it's actually sucking down the flue instead of letting it rise up because of the natural draft, because of the hot gases. So we're going to set my house up here. We're going to switch the, I'm going to make Bill Graber the presenter. He's going to run the camera, and I'm going to demonstrate these measurements here in my house. Okay, so here we are in my furnace room. I've got my DG-8 set up, and I want to know the pressure in this room with respect to outside. So this pressure that I want to know, the plus tap is connected to this room, which is nothing. And on the minus tap, this is a hose that goes out through a basement window to outside. And if we let this stabilize for a minute, you can see that we're getting about minus 3.6 pascals. This is, again, this is the stack effect in Minneapolis today.
It's continuing to shift.
Oh, okay. Yeah, so this may shift around some. And I want to demonstrate with the smoke here. This is the draft in my water heater, and you can see that the smoke is going up the flue. I've got all my exhaust fans in the house are turned off, and this is drafting properly. The water heater's not running right now. Okay, now I've got a tube that I can use. Now I'm going to measure the pressure in the flue. So now I want to know the pressure in the flue, so I'm going to connect the tube to the plus. That'll tell me the pressure inside the flue pipe with respect to the room. You see I'm going in there, and I'm measuring about minus 6 pascals. That tells me the pressure inside the flue pipe is lower than in the room. That's good. That means that the flue pipe is sucking the exhaust gases up, or that the room is pushing the exhaust gases into the flue pipe, whichever way you want to look at it. Now I'm going to go down the hall. I'm going to connect this back up. The outside. So here we're back to our natural draft, and I'm going to put this on a 5-second average. It'll take 5 seconds to fill up the buffer there. So this will just be a little bit more stable than reading the screen directly on the DG-8. And now I'm going to walk down the hall, and I'm going to turn the clothes dryer on. We're going to see what happens to the pressure and what happens to the draft.
I'll stay here and we'll just watch the DG-8 for kind of the fast response. Yeah, and there he goes, and you can see it dropping. That's just one big exhaust fan, essentially.
Okay. So now we've dropped the pressure by about 2 pascals, give or take, right?
Yeah.
Okay, that's just from turning the clothes dryer on. It's sucking on the house and makes this pressure get lower.
Remind us, Steve, 2 pascals, you know, I mean, that's like it's 25 pascals to 1/10 of an inch of water, right?
Yep, that's right.
Yeah, so just as a reference point for people, if they think in inches of water column, yep. I mean, this is like 1/100 of an inch.
Yeah, this is a tiny, tiny pressure.
Okay.
Okay, so now I'm going to check the draft again, and you can see we still have the smoke going up the flue pipe, so we're still good. But now I'm going to put the water heater on pilot just so it doesn't go on, because I'm going to intentionally drop the pressure down by turning on. I'm going to go upstairs and I'm going to turn all the exhaust fans on. I've got 3 bathroom exhaust fans and a range hood upstairs. I'm going to turn all of them on, and you're going to see this pressure drop. So Bill's going to stay here. It'll just take me about a minute to turn all those on, and we'll see what happens.
Okay. And while Steve is doing that, I'll just zoom in so that we can watch the, response from the DG-8. Or we could watch a Bluetooth response on our iPad or, Android tablet, whatever you want to Bluetooth connect to. But we'll start to see this drop as he turns on each successive fan. And like he said, the dryer's on, which is 1, but now there's going to be 4 additional fans of varying capacities, 3 bath and 1 kitchen hood. That was quick.
Okay. So now we've turned all the exhaust fans in the house. We've got the dryer running and the kitchen range hood going. Now let's see what's happening to the smoke here. Now you can see that the smoke actually blows out. So if this water heater were to fire up right now, the exhaust gases would just pour into my basement. I don't want that. So you can see what's happening with the smoke. I'm also going to measure it with the manometer, just so you can see that the same pressure measurement that I made before, which is done by putting this on the plus tap and then putting it into the flue pipe. Now I'm getting a positive pressure. That tells me there's more pressure in that pipe than there is in this room.
And you're saying that because the other tap, the negative, you know, you've got it hooked to the positive in the pipe. This negative is just open to this room.
Yep.
So that pressure is the difference between your flue pipe and the room.
Yep.
You want that negative and you're seeing a positive.
Yep. And you can also, if you've looked at this before, there's actually a telltale sign here that this has happened before I knew much about combustion appliance safety. You can see that the insulation on this pipe has been melted by the water heater backdrafting. That's a telltale sign that this has happened before. Now I know a little bit more about it and I know how to do it more carefully, but really we should be thinking about what's the permanent solution to a problem like this. And there's really 3 choices. You can use a power vented gas water heater that has a fan on top that will blow the gases out, or you can replace it with an electric water heater. Either a heat pump or a straight resistance electric water heater will not have this risk. Part of the problem that I face here is, if you take a look over here, Bill, this is what we call an orphan water heater. When this house was built in 1958, the furnace and the water heater would both have gone up this chimney. But the furnace was replaced sometime in the 1990s with a furnace that vents through the PVC. That means that the furnace is not keeping the chimney hot all the time. And so now the water heater has to provide draft on its own, which is hard for a water heater to do because it doesn't produce nearly as much waste heat as a furnace would have. So this is what we call an orphan water heater. And this is a situation where you're more likely to have problems like backdrafting. And if you have an orphan water heater, you should absolutely have a carbon monoxide alarm, and even be thinking about a low-level carbon monoxide monitor in addition, because the high-level alarms are federally regulated and they don't alarm until you get to a fairly risky, fairly dangerous level of carbon monoxide. But I've actually just ordered a low-level CO2 manometer from TruTech tools, so that I know if this is happening, I will see a spike in my carbon monoxide in the house if this starts backdrafting unintentionally.
You know, Steve, what occurred to me is I don't think we turned on your basement bathroom fan. Maybe we did.
I did.
But maybe we could go over and while we're live here, you could show that and then we come back around and explain what you're doing. But you can use the exhaust fan flow meter for that.
Yeah.
That sound okay?
Yeah, let's do that.
Yep.
Get the DG-8.
Oh, yeah.
Okay, so now we're actually going to measure how many cubic feet per minute it's taking. If we measured this individually, this bathroom fan would cause the house pressure to drop by maybe a half a Pascal or a Pascal on its own. And this device is an exhaust fan flow meter. This allows us to measure how many CFM are going through this exhaust fan. And the way you do this is it's got 3 positions. You always start in the E1 position. Just remember 1, 2, 3. And you keep closing the door until you get a pressure that's between 1 Pascal and 5 Pascals, or 8, or yeah, -1 and -8. You can see I'm getting about -0.4. That means I'm not getting a good measurement yet.
So I'm going to close it to the next position, E2. And now I'm getting about 1.8 pascals.
Okay, so what does that mean?
So now I can look at the chart that's right on the side here. And I measured 1.8 pascals. And I'm in position E2. So that means I've got about 28 CFM going through this exhaust fan. I've measured all the other exhaust fans. I've got one that's 86, one that's, the other two are about 50 CFM.
Okay.
So all together, you know, I've got over 100 CFM of exhaust fan flows.
That just in the bathroom, not including your kitchen.
Yeah, right.
Yeah,
Now,
okay.
typically your exhaust fans are going to be lower flow. The big flows are typically your range hood and your dryer, but those are pretty hard to measure. We can talk about ways to do that.
Yeah.
So this is,
yeah, go ahead.
so this is just intended as an introduction to combustion safety. There's protocols. We have a really good webinar talking about exactly how to do this. And that will guide you in learning more about combustion safety. Make sure you're not putting occupants of houses that have appliances indoors at risk.
Yeah, really shows the value of what Bill Spohn has done too with this all electric approach.
All electric, there's no risk here.
Yeah. I've heard some people mention electrify everything. I've just heard it somewhere.
Yeah.
All right, I'm going to pass it back to you if you want to go to your.
Yep, sounds good.
All right.
So we've got just a few minutes left here, and we want to talk about combustion spillage. We've set up the house, we measured, and we showed you what happens when you backdraft an appliance. Okay. And as I mentioned, this is a significant safety concern. It's the case that still, you know, people die every year from carbon monoxide poisoning. So absolutely be sure that you have a carbon monoxide alarm at the very least, and be thinking about a low-level carbon monoxide monitor. Okay. So this is an example of the protocol, how to do a more detailed and rigorous test. There's 3 steps here. Normally you start with all the exhaust devices on, then you turn the air handler on, and then you opening and closing the doors in the house can also affect whether you have enough pressure to backdraft the water heater or other devices. And typically there are not only protocols, but there's rules about how much is too much difference, or how much change in the room pressure, or how long you can backdraft the water heater. If the water heater goes on, I should mention that many times the heat coming out of the water heater, if it goes into full fire, is enough to restart a good draft, even if the exhaust fans had caused it to start backdrafting for a while. Okay. So I'm going to skip ahead here past HVAC static pressures, and we just want to take a look at the exhaust fan flow meter. So this is the device I was showing in my bathroom that's used to measure airflow from exhaust fans. There's the 3 positions, each one, you know, the smaller hole has the smallest range. So it measures from 10 CFM up to about 124. It's very simple. You just put it over the exhaust fan until you get a pressure between 1 and 8, or -1 and -8 pascals, and then look up what flow that means on the right on the chart on the side. Yeah, so the procedure is just like I mentioned there. I think we want to go ahead and maybe I want to leave a few minutes for questions. So rather than go through the other measurements, I think we're maybe going to stop right here. We've got about 8 minutes left for questions. Does that sound good?
I think so, Steve. And I do think we just need to have another part 2 to this.
Yeah. Yeah, it was a lot of material.
There's a lot to do. You know, we learned, you know, how to do live testing in this. So I think we could do a part 2 to this.
You saying it'll be smoother next time?
I'm guaranteeing it. Steve, there were some questions that were in the Q&A here, and I think they were asked during your portion here. Wouldn't the air handler wouldn't the air handler make that spillage even worse if you had any duct leakage to the outside?
It depends on if you're leaking from supply to outside or from return to outside. If you're leaking from the supply to outside, it's going to depressurize the house, and yes, that'll make it worse. Now, I've measured in my own house. We had the furnace off just to not make things unclear, but I have a little bit of leakage from the return ducts in my house, so I'm sucking a little bit of outside air into my return ducts, just because we've got they're between the floor and where that floor meets the rim joist of the house. I've got panned joists like they did back in the day, and that means I'm sucking a little bit of outside air into my return. That means my house is slightly pressurized when the system runs by about a Pascal. So it depending on whether you're leaking from the supply or the return, it could be better or worse when the system is running.
Gotcha. And then there was one more. The convective forces will greatly overcome those small pressure differences you're seeing. Did you have the water heater on or off?
No, we put the water heater in pilot just because we didn't want to backdraft it. So I think this is from Gerald. Yes, Gerald is right. The hot water, or sorry, the hot gases when they start leaving will very often overcome this. But the question is, how long will that take, and how long will it spill into the room? So there are protocols that are given. Paul Francisco is one of the experts out of Illinois, who can tell you, how long is it okay. There are actually regulations that are followed by weatherization personnel and other organizations that say how long is it okay to be spilling into the room before it reestablishes the draft. Because if you're depressurizing bad enough, it won't ever reestablish the draft, because as the flue gets colder and colder, and of course it depends on the outdoor air temperature too. If it's really cold, you can get a thermal siphon, because the whole flue gets cold, stays cold, and then if you can't reestablish the draft to get it going again.
Okay.
So question here, where would you locate the CO or low-level CO monitor? I think the federal regulations are that it's in the lowest occupied level. So we have a bedroom in the basement, so that's going to be considered an occupied level. So we would put it in probably a basement hallway rather than right in the furnace room.
I'll actually add to that a little bit, Steve.
Okay.
So I would say the first CO alarms you get go outside the sleeping rooms on each floor. Then if you have the budget, go inside the sleeping rooms. And something to keep in mind, CO is neutrally buoyant. So mount them at head level so you can see them and read the display easily. I would not recommend mounting them in the furnace room in the kitchen. They'll produce annoyance alarms. And then it's very possible that the resident will shut them off or take the battery out because they're getting annoyed because it sees a little bit of CO for a little while. So it's really about the sleeping rooms, because that's where CO takes its toll.
So I see David Daly's asking a question. I've seen appliances that fail spillage but pass draft. What could cause this? I actually don't know. That's a question that we can refer to one of the experts. I think somebody like Paul Francisco could answer that question. We can, if you reach out to us with an email, we can get an answer on that for you.
There was another comment, CO rises unless it's below freezing. The technical answer that I know from my physics research and expert witness work as a CO expert is that CO moves with the air. That's the simplest way to think about it. It is not a heavy gas. It's got almost the same density as air.
Okay, great.
That's been a question out there on different Facebook groups, and I've been trying to answer it directly.
Great. So somebody says, in Maryland, all orphan gas hot water heaters are required to have a stainless steel liner. I think the stainless steel, I assume they mean a stainless steel liner in the masonry chimney, and that really, really helps. My house has one of those as well. The liner means that there's a lot less that you have to keep warm to make it draft properly.
A lot less volume of air that has to be turned into buoyant air.
Yep, exactly.
And I think that's like BPI for a while had a big push for what they called orphaned water heaters when high efficiency furnaces were put in for weatherization purposes. And water heaters were left orphaned inside a big chimney and having to try to create enough thermal energy to create buoyancy and vent.
Yeah. Okay. Well, Bill, I sure appreciate you inviting us to do this webinar. I hope everybody learned a lot and understands that there are a lot of things you can measure with just tiny pressures in a short amount of time that can point you in the right direction for flagging some safety concerns or understanding house comfort better. So thanks so much.
Yes, thank you, Steve, too. And it's really neat to see the DG-8 come out. You just power it up and it's there. The numbers are there. You hook it up to the free app. You've got time-based averaging on it. It's just a really nice tool to add to your toolkit. And it does more than these house pressure tests, of course. It's pretty much a universal manometer, precision universal manometer. So thanks for creating it.
Yeah, well, thank you. Yeah, so just to mention along those lines, it measures up to 10 inches of water. So you can use this on the static pressures. You could use it on gas pressures that are, as long as they're under 10 inches of water. It's very flexible, can use for higher pressures too, not just the tiny pressures.